Hello, my name is Hugo and I present about the paper in RFIC-oriented flow for planar inductors modeling and generation aiming open source PDKs. This presentation will cover the main topics of the paper. And starting with the introduction, we have been seeing the democratization of the IC design in semiconductor industry. So recent developments in open source silicon reflect the necessity of the democratizing the integrated circuit design process to address challenges in semiconductor industry. Because before that, only the commercial tools allowed the professionals to do the IC design. This democratization also helps to solve the problem of the global chip shortage of professional. Moreover, we can attract new talents through these initiatives, fostering innovation, reducing costs, and accelerating the design to production cycle. In this community, we have a lot of collaborative channels where the community can suggest flows, discuss about bugs, problems, and etc. The tiny tape out is a good approach for low-cost IC prototyping, and it's a nice methodology for low-frequency digital and analog IC projects within the open source ecosystem. But the RFIC has a lack of consolidated flow, and the RFIC are widely used in smartphones, Internet of Things, 5G, and quantum computing. The RFIC design has a lot of challenges, but one of them is modeling of passive components, such as inductors. So this paper proposes an RFIC-oriented flow using the ASIC to model the inductor, and this inductor will be inserted into this parallel LC filter using Sky130 open-PDK to operate in ISM 2.5 GHz. And all the flow was used using open source tools to run the simulations and to do the verification of the circuit, such as Magic, NetGen, Xscheme, and GSpice. So about the inductor modeling and proposed flow, we have the inductors P equivalent, which is depicted here, and this equivalent represents the integrated inductor, where the R is the resistance of the wire that forms the inductor, RS and RS2 account for the substrate losses, CS1 and CS2 represent the capacitance between the inductor and the substrate. So this model offers a more accurate representation of the behavior of the integrated inductor. So we proposed an inductor modeling flow where we start with the ASIC. So we use the ASIC with a pre-made Sky130 PDK technology file, and this function called opt-SQ to create a 1 nanohenry square inductor with optimal key factor, occupying an area of 0.016 square millimeters. which is depicted in this figure. Next, we run the PIX function at 2.5 GHz to determine the P equivalent of the circuit, along with the inductor's key factor and the self-resonant frequency. And finally, we used the CIFSAVE to export the layout of the inductor as a CIF file. So as you can see here, the EasyTick to create the inductor, its inductor's P equivalence is used with Xscheme plus ngSpice to run the simulation, and the CIF file is used in the magic to create the mag file. So here is the inductor simulation of the impedance, imaginary part and real part. At the self-resonant frequency of 2758 GHz here, we can see a maximum impedance in real part and a zero imaginary part. In this self-resonant frequency of 27 is about 10 times greater than the ISM 2.5 GHz, which is the frequency of the LC filter. This ensures the inductor's proper operation within the frequency band, this frequency here. So about the LC filter, we proposed this flow. This flow is similar to an analog IC design flow. We have the inductor P equivalent to the Xscheme plus ngSpice to run the pre and post layout simulations. There is the magic to create the layout, run the packs, and the NetGen to run the LVS, layout versus schematic. The schematic used of the LC schematic contains a capacitor of the library and the inductor, where its P equivalent are described inside this subcircuit. But to insert the inductor inside this flow, it was done some modifications. The first modification is about adding the R-metal 5 layer to one port of the inductor, as you can see in this figure. This R-metal 5 in the physical level is just a simple metal, just as metal 5. But when Magic extract the netlist, this R-metal 5 is extracted as a resistor. So this resistance prevents a short circuit because the inductor is treated just as a simple wire. So this resistor prevents the short circuit between P1 and P2. So this circuit is used to LVS purpose the capacitor, see the same capacitor, but this resistor replaces the inductor. The second modification is about the packs, where the inductor was removed to run the packs because the parasitics of the inductor already are in its P equivalent. So the packs was performed just to extract the remaining parasitics of the circuit. Thus, the sum of the parasitic of the inductor, represented in its P equivalent, plus the parasitic extraction of the layout, give us the parasitic of the LC filter. And here there is a simulation of the LC filter with the pre and post layout. And we can observe that the LC filter reaches its maximum post layout impedance at the frequency of 2.45 GHz here. And this shows a shift of 50 MHz in comparison to the pre-layout simulation. Moreover, we can see some changes in the magnitude of the impedance, imaginary part and real part. We can see a decreasing of the magnitude. And finally, about the conclusions and future works. This paper demonstrates the design of an LC circuit to validate the feasibility of the proposed inductor modeling and generation flow, which can be integrated into open source IC design flow for RF circuits. So this proposed flow leverages popular open source tools for analog IC, such as XKey, Magic, alongside the ASIC. So we inserted the ASIC inside the flow and did some modifications. Although the RFIC design encompasses more than just inductor synthesis, this step is critical for progressing towards a more comprehensive RF open source IC design flow. So as suggestions to future works, we suggest the use of some tool alternative to the ASIC to model the inductors, transformers, capacitors, the integration of electromagnetic solvers within the design tools, support for additional open PDKs such as IHP, global foundries, and methods for indirect testing using tiny tapeouts to support these high-frequency circuits. And finally, we have the references. So thank you.